very less, and lightweight, okay, and of course easy to manufacture. So if I give the antenna after a design, if I give the antenna to a manufacturer, he can manufacture thousands of antennas in 2 or 3 days. So bulk manufacturing is very easy, cost is very less, low profile, lightweight. Not in addition to these things, it is very easy to integrate into the compact devices. Whatever device we talk about, it may be a mobile phone, it may be your smartwatch, it may be your laptop, or it may be any wearable device. So microstrip antennas, because of their lightweight, small size, low profile, easy to manufacture, low cost, in addition to all these things, conformable. Conformable in nature means, what is maybe conformal? Means the antenna. Just look at this my patch antenna, which is printed on any curved surface. Because of the conformal nature, these, they are flexible. We can fix it on any surface. It need not be a plane. It need not be a plane on which you are going to fix. It can be any curve. Look at this, the aircraft, or look at your missile. The surface is not plane. It may be curved, or it may be any shape. So that is one beautiful, unique feature of microstrip antennas. Okay, as I told, the participants know little bit about the microstrip antennas, then this session will be still better, will be very good. Okay, yes, that is about the microstrip. Now we are going to talk about where to use this. Yeah, yes, I told na, these microstrip antennas can be used in many applications like Wi-Fi, Bluetooth, mobile communications, GPS, satellite, whatnot. So because of the advantages or the benefits which I mentioned in the earlier slide, the microstrip antennas are being used in many areas. Though the frequency of operation for these applications are different. Your Wi-Fi operates at 2.45 GHz or 5 GHz. Your Bluetooth operates at 2.45 GHz. Your GPS, the L1 band or L2 band, global position system. The antennas, microstrip antennas also can be used on the satellite systems. Okay, why actually, though the microstrip antennas came into picture for 2 to 3 decades back, why so much of interest the researchers are showing? Because still research is going on. One major disadvantage with once upon a time, not now, is the bandwidth limitation. So the antenna operates over a little band, small band of frequencies. That is one thing. And how to minimize, that is another work that people are doing the research. And how do you integrate this with advanced technologies like 5G, 6G, and IoT? Of course. Okay, so this is the main major areas on which people are working, especially in the microstrip antennas. In addition to that, reconfigurability. Now today's topic is actually reconfigurability. We should not forget that major topic which we are focusing on today. That is, yeah, reconfigurable antennas. What do you understand by reconfigurability? So generally, once an antenna is designed, fabricated, and installed, it will operate at one particular frequency, or it gives a particular pattern, or it gives a polarization. Anyone can respond, those who are online. Can you tell me what are the important parameters of an antenna? Once I design, what do you look for? Anyone who knows?
Radiation pattern, sir.
Yes, radiation pattern, Mahbub Basha. Yes.
Return loss, sir.
Emma?
Return loss.
Return loss. Return loss is nothing but SON characteristics. We
Yes,
talk
sir.
about,
Yes.
yeah.
Yes, sir. Yes, sir.
Yeah, frequency of operation. So
Beam
from
width,
S,
sir.
beam width. Beam width is obtained from the radiation pattern. Yeah, correct. One more important thing you forgot. Polarization. Polarization.
Yes, sir.
So these three are the very important parameters for any antenna which we look after we design. After design, what do you look? Whether the antenna is operating at the frequency that we design, or whether the antenna is giving the required pattern, or whether the antenna is giving the desired polarization. These three are the major parameters that every engineer looks after their design. Now, in the reconfigurable, what we do, yes, how do we adjust these things dynamically? After I designed, I must be in a position to adjust these parameters dynamically. I have fabricated, I have installed. Even then, I am in a position to change the frequency, change the polarization, change the radiation pattern. So that what we are talking about reconfigurability. So reconfigurability is the way we change the, please understand clearly, reconfigurability is the method how we change the parameters of the antenna dynamically based on the system needs. I have designed the antenna to operate at 2.4 gigahertz, but I want it at 2.2 gigahertz. But what should I do? Can I remove the antenna and can I put another antenna? No, that is not a reconfigurability. So after fabrication, I must be in a position to change the frequency of operation, not only the frequency of operation, as the participants told, we look for the radiation pattern, we look for the frequency of operation, we look for the polarization. These three are the very, very important parameters. Of course, beam width to bandwidth to those things, of course, come later. But these three are the very important parameters. Okay, so look at this. One is the frequency, the second one is the polarization, and third one is the first one is the frequency, the second one is the pattern, and third one is the polarization. So our session, 1.5 hour, 1 hour session is mainly focused on how do we change the frequency of operation. Yes, that is one through S11 characters. How do we check the frequency of operation? Frequency of operation of an antenna is known through S11 characteristics or return loss characteristics. This is the first one which we have to look. The second one, as you told, radiation pattern. Radiation pattern is generally based on the structure of the antenna, or sometimes we can change the phase. Phase also phase, because when I use an antenna array, people who taught antennas might have known how the radiation pattern of antenna can be changed dynamically. The phase of the signal given to the each and independent antennas will change the radiation pattern, not only the direction but also the shape. Okay, can be changed by changing the phase. So how do we change it dynamically? That is, and polarization. The antennas generally provide linear polarization, or it may be circular polarization or elliptical polarization. Elliptical polarization is a special case of circular polarization. Generally, it's very difficult to achieve circular polarization. Slight variation in the circular polarization, we call it as elliptical polarization. There are several advantages of having circular polarized antennas. If I use linear polarized antenna, if the antenna is horizontal, the transmitting antenna is horizontal, receiving antenna also must be horizontal. If the transmitting antenna is vertical, receiving antenna also must be vertical. But if I use a circular polarized antenna or elliptical polarized antenna, the orientation of the antenna does not play any role in getting the signal. So that is the use. That is one important advantage of using a circularly polarized antenna. The antenna which we use in the mobile phone is a circular polarized antenna. Because when we attend a call, is there any guarantee that we keep the antenna vertical or horizontal? No, we keep changing the direction of orientation of the mobile phone. Even then, there is no change in the amplitude of the signal or quality of the signal, even if you change the orientation of the mobile phone, because it is a circularly polarized antenna. Okay, so where do you use? Okay, the concept is how do you change these parameters dynamically? Oh, yes, these are used in the multi-standard, cognitive, and adaptive wireless systems. This concept is very essential for multi-standard, cognitive, and adaptive wireless systems. What do you mean by multi-standard? Means, see, a system can operate at different frequencies. Okay, it is multi-standard. You know, you might have heard about cognitive radio. So the cognitive radio, I think some of you might have heard about the cognitive radio. It is for effective use of spectrum. You know, spectrum is a limited one. We don't have large bandwidth. We have limited bandwidth. You are supposed to use that spectrum effectively. So what should you do? I should look for a channel which is free, not in use. Then I will transmit the signal. How do I know? So first of all, I should know which band of frequency is vacant, the channel is free. Then I should transmit the signal at that frequency. So if I wanted to send the signal at that frequency, do you think that the antenna is designed to operate at that frequency? Maybe, may not be. So my reconfigurability concept allows you to operate the antenna at any frequency within the band. So that is one important concept. When we are talking about reconfigurability, definitely my cognitive radio comes into picture. In cognitive radios, 100% we use reconfigurable antennas, because the antenna should be in a position to radiate the band of frequencies which is not in use. So I want the antenna to radiate at particular frequency. Okay, so at that particular frequency, the antenna should radiate. So that adaptive wireless systems. Okay, so this is one the important concept that our concept is mainly focused on. Okay, now look at this reconfigurable states. This is a general structure which I have shown. Okay, this is my feed. Feed is at the place where we give the signal to the antenna. This is side view. This is the patch. Let us assume, but it is a general concept. Don't think that the switches are placed here. So when I have, let us assume, two switches, by controlling these switches, we will talk in detail about what type of switches are being used. How do you control? The main discussion in this session is how do we change the frequency? How do we change the polarization? How do we change the pattern dynamically with the help of some switches? What type of switches are being used to control these things? That is the main point of discussion in this session. Let us assume if I use only two switches, I have two switches means I get four possibilities. Switch 1, switch 2, off, on, on. So when I have this is on, this is off, it will operate one particular frequency. This is off, this is on, switch 1 is an on, switch 2 is an off, one frequency. Both are on, it gives another frequency. That is the one important thing that you have to understand. So the frequency of operation of the antenna can be changed by controlling the switches. Yes. Yes. No. Now, why actually we need to go for this reconfigurable antennas? What actually motivated us to design reconfigurable antennas? Mahbub Basha, I think. Mahbub Basha.
Sir.
Yeah. Okay. It is your mic only. Okay. ఒకసారి మ్యూట్ చేయండి మళ్ళీ ఎప్పుడైనా కావాలని మాట్లాడవచ్చు.
ఓకే సార్.
ఓకే, థ్యాంక్ యూ. యా, yes, what actually motivated us to go for the reconfigurable antennas? Look at this multi-standard system. It is a traditional system. Assume that system is operating at 2.4 gigahertz, 5 gigahertz and 6 gigahertz. If I don't use the concept of reconfigurability, I should use 3 different antennas. If I use a reconfigurable system, same antenna, only one antenna that can operate at multiple bands, that will give different patterns. So that is the motivation behind going for the reconfigurable. So that the number of antennas that on the system can be reduced. The main idea is instead of going for 3 antennas or 4 antennas, a single antenna can do this work. That is the ultimate idea of the reconfigurable antenna. So it supports multiple frequency bands in a single device and reduces the number of antennas on the system, and also physical footprint. Because I have only one antenna, obviously the space which is meant for keeping the antennas is reduced. Okay, so obviously it helps us to steer the beam steering is possible. Efficient use, when I'm talking, as I mentioned, when I'm talking about reconfigurable antennas, we should not forget about this cognitive radio concept, where the spectrum is used efficiently. Okay, when something is not being used, why should I keep it idle? My system will identify which band is not in use, then I will use that. But my antenna should be in a position to radiate na. So here reconfigurability, through reconfigurability, I make this antenna to operate at that particular frequency at which the channel is free. Okay, of course, which enhances the communication robustness, because the system which I designed, which is not which is designed for particular band of frequencies, it is not robust. When I design a system which can operate at multiple bands, definitely it gives robust. Okay, that is the motivation behind designing reconfigurable antennas. Yes. Now, what are the various parameters that we can change? Yes. One is the frequency. Of course, whatever I am trying to tell here it is written in the matter, of course, in the form of a figure also I am trying to show. So, in the entire session, we will talking about the frequency or polarization or pattern. Sometimes I can combine these things also. Don't think that only I can change the frequency dynamically. Don't think that only polarization can be changed at a time. Don't think that only radiation pattern is changed at a time. If I change the frequency, it may also possible to change the radiation pattern. That we call it the combined. Actually, we meant for only changing the frequency, but it is also possible to change the pattern. Okay, that is what you call combined. So reconfigurable antennas, what are the parameters? One is the frequency. What we do, we will change the frequency, radiation pattern, not only the direction but also shape. Don't think that pattern reconfigurable antennas will change only the direction. Don't think that only the direction. We should think about the shape. Shape can be changed, direction also can be changed. We call it as a beam steering. Yes, beam steering. And one more thing is the polarization. The antenna can provide linear or circular elliptical. It is possible to switch among these three polarizations. Okay, I want only linear. Yes, it is possible. But I don't want the antenna to operate in linear. I want the antenna to radiate in circular polarization. It is possible. Or elliptical. It is possible. But it is not so easy as we think. Okay. So there are number of things that we need to take care to make the antenna to operate at multiple frequencies, multiple bands, or multiple polarizations. Okay, how do we change it? How we are taking the help of the switches to make the antenna to operate at multiple bands. This is the point of discussion. Now combined, as I told, now combined. So we can combine these parameters adaptively. Okay, that is simultaneously we can control these parameters. One is the frequency, pattern, and polarization. I hope that the participants are well aware of on what parameter the frequency depends. Okay, but it's very good. So frequency, as you told, the frequency of operation can be known from Ritter loss or S1 characteristics. Radiation pattern depends on the structure, and polarization also the way we feed the signal, the way the current flows through the antenna will decide the type of the polarization. Okay, first of all, the participant should know a little knowledge, should have little knowledge about these concepts. Yes. Now, based on these things, my reconfigured antennas are broadly classified into 4 categories. One is frequency reconfigurable antennas, pattern reconfigurable antennas, polarization reconfigurable antennas, and hybrid reconfigurable antennas, where all these things are combined. Multiple parameter reconfiguration simultaneously. This is the way I represent when I am changing the frequency or frequency reconfigurability. This is the symbol generally I use for representing the pattern reconfigurability. This is the symbol generally I use for, this is not standard, but in this presentation, I use this notation when I'm changing or reconfiguring the polarization. When I combine these things, of course, look at this, there are 3 things. This is the polarization, this is the pattern, this is the frequency. This is the combination. Okay. Yeah. So state 1, state 2, state 3. When the switch positions are in one state, it operates in one frequency. When the switch positions are changed, we call it as the patch antenna, or the antenna goes into stage 2, or it may be combined. Okay. So as I told you, there are different applications. What is the applications? One is the antenna operates at multiband, beam steering. Of course, it can be used for satellite communication. Cognitive radio, as I mentioned, it's very important application of my reconfigurable antennas. Yes. Then how do you achieve this one? Okay, we are talking about the parameters. Based on the parameters which we are changing, the antennas, reconfigurable antennas, RAs, we call it as RAs, are broadly classified into 4: frequency, polarization, and pattern. But how do you achieve this? Yes, this changing or controlling the parameters is achieved through electrical or mechanical, through material, or through optical, through metamaterial. Okay, so now how do you control these switches? There are, through electrical switching, we use pin diodes, MEMS, varactors. How do you control these parameters? Through mechanical. One is actuators and switches. Even material tuning, through material tuning also, it is possible to change these parameters, whatever we discuss, like frequency, pattern, and polarization. So smart materials are, liquid metals are there. Very beautiful concept, liquid metal. Okay, by injecting some, we'll see in detail later slides. The other one is optical control. By focusing light on some materials, it is possible to change the phase. Please understand, especially for beam steering, phase comes into picture. Those who taught antenna wave propagation, those who taught EMTL might have known about these things. Phase plays an important role. When I use multiple antennas, with what phase the signal is given to a particular antenna matters to change the pattern, shape, or the direction of the radiation pattern. So that is possible. How do we change the phase? Phase change can be done through optical also. But when I use optical, I should use those materials which are sensitive to those phase. So when light falls on it, the phase should change. When phase is changed, the pattern direction should change, or the shape should change. And of course, last one is metamaterial approach. Metamaterials like your EBG, electromagnetic band gap structures are there. Your artificial magnetic conducting surfaces are there, which we call them as metamaterials. Now the research is going on metamaterials. Metamaterials are the materials which are not available in nature. By putting some patterns on the substrate, it is possible to get metamaterials. Anyhow, that is a different topic of discussion. But our focus is mainly on how do we change these parameters, frequency, polarization, and pattern through electrical means, through mechanical means, through material means, through optical or light, or through metamaterial. That is the point of discussion in this session. Yes. Now, first one is electrical. So when we talk about the electrical, yes, my pin diode comes into picture. So whoever talking about the reconfigurability, they should talk about pin diodes. Yes. Now, okay, can anyone tell what is actually P stands for, I stands for, N stands for?
P intrinsic N, sir.
Yes, yes. Is a
P
P type?
material intrinsic N.
Yes, checker point is yes, yes. P type, intrinsic type, and N type. It is actually meant for RF switch. We were talking about, we know about PN junction diode, but pin diode is actually meant for RF switching. Okay, because my ordinary PN junction diode cannot work at RF frequency, radio frequency. The switching speed is not enough. So generally we use pin diodes for changing the state of the antenna. Okay, na? So here we, by turning on or by turning off, of course, biasing is required. This is first thing what we have to understand is when I wanted to change the frequency by electrical means, I should use some devices. What are they? One is the MEMS, pin diodes, and of course the varactor diodes. So biasing is required because they are the solid state devices. Without biasing, they cannot work. One burden on us is how to give the biasing. Biasing, designing a biasing network is very difficult. It is not so easy as we think. Okay, so of course that is a different concept. But the only thing which you have to understand is the pin diodes when I use to change the state. Okay, biasing is required. On means yes, low resistance it provides. Off means high resistance it provides. The current. Look at this second statement. What do you do by turning on or turning off? Yes, I am changing the current flow path. We will see one or two examples. What happens when the PIN diode is turned on? What happens when PIN diode is in off condition? Okay, so that. But key advantage is very compact and high speed. So the beauty of my PIN diode is high switching speed and compact integration. Reliable, no doubt. Okay, so that is the reason why people use widely. Many of the cases, people use pin diodes. Okay, to control the operation of my antenna. Okay, so here we control the DC through DC bias. I can control through voltage. Even RF MEMS also, micro electromechanical systems. There also I use the voltage. Of course, the way I turn it on, turn off is different. In varactor, is a variable capacitor. When I change the voltage, what happens? Can anyone tell what happens to the varactor diode when I change the voltage given to the varactor diode?
Capacitance changes.
Capacitance changes. Okay, na? So we by changing the capacitor, by changing the voltage, capacitor changes. When capacitance changes, the frequency of operation changes. We will see little later about this varactor diode when it is loaded onto the patch, how it changes the frequency. Wonderful concept, varactor diode. Yes, now look at this MEMS. So MEMS is actually micro electromechanical systems. But if you look at the structure, what happens when the biasing is given? Look at this, when it is an off condition. When it is an off condition, yes, is there any connection between RFA and RFB? No connection. Here a cantilever beam, look at this beam. It's like a cantilever beam. When supply is given, this will come down, this will come down. Now let us see how a contact is made. When supply is not given, what happens when it is like this? Okay, so only thing is you have to understand how much insertion loss it gives. Okay, when signal is given here, taken here, is there an insertion loss? So that you have to take care. What is the isolation? What is the insertion loss? The switch is only to connect RFA A and B, but this should not absorb, or there should not be any power loss here. So my MEMS switch gives very low insertion loss. That is one advantage of my MEMS. High isolation. High isolation means when it is an off condition, there should not be any leakage, and how much power is consumed. So when I am talking about these switches, the components for controlling these parameters, what are those three things which I talked about? One is pin diode, the other one is MEMS, the third one is varactor diode. Which one we have to choose for a particular application? That talks upon the application, which one you want. You wanted to go for frequency or pattern or something else. Okay, so suited for this, MEMS is suited for frequency, pattern, and polarization. For all these three, it is suitable. Okay, as I told already, when these devices use a moving micro scale mechanical component, we call it the cantilever beam. This cantilever beam will be touched so that contact is made, or break or create is done through electrical connection. Okay, so this is the symbol, this is the component of my electromechanical switch. These dimensions are in micrometers. Yes. Now look at this. How I use MEMS. Let us assume this is my E-shaped patch antenna, maybe designed to operate at 8.5 gigahertz or 8.9 gigahertz or 2 gigahertz. Don't worry about it. But my idea is what happens when I look at this. I think you are able to see where I am connecting these MEMS switches. Look at this. Look at this. Look at this. Look at this. When diode is in off state, the antenna operates at, look at this, operates at, so first of all, you should understand what happens when the diode is on, what happens when the switch is on, current path is different. Current flows in longer path, operates at low frequency. Current flows shorter distance, the antenna operates at a high frequency. Yes. Now tell me, look at this one, look at this one. When the switch is on, current flows like this. When the switch is in off condition, the current flows in different path. Now that is the reason. Look at this. The blue color, when switches are in off state, current path is more, and frequency of operation is 2 and 2.6. When they are off, look at this. Yes. Now they are operating at high frequency. Okay. So that is the way I change the frequency operation by turning on or turning off those MEMS switches. But switching speed is approximately 10 to 100 microseconds. Isolation is more than 30 dB. So what is the guarantee that when the switch, it is a switch na, even when it is in on condition, some current flow. What is that loss? What is that isolation? That is also an important parameter when I choose a particular component for reconfigurability. So what is that switching speed? 10 to 100 microseconds. On to off to on takes approximately 100 microseconds. When the switch is in on condition, how much loss will be there from input to output? Approximately 0.2 decibels. When it is in off condition, what is the isolation between the input and output? More than 30 dB. It's as important as insertion loss. Yes. Now look at this advantages, limitations. When I'm talking about MEMS, yeah, linearity is very good linearity, and power efficiency is good. But only problem with the MEMS is complexity, fabrication complexity is more. Okay, that is the only problem with the fabrication it's not so easy to fabricate, and the initial cost is also very high. That is the limitation of my MEMS. Of course, one more thing is also there, limited speed compared to your solid state devices. What are the solid state devices like your pin diode? Okay, I think, can you tell me one more disadvantage with MEMS? Anyone? One disadvantage, because it's mechanical. A cantilever beam will be touched, will come down, will go up. So the lifetime is a major concern, because electronic switch okay, but when I'm talking about mechanical switch, since there is inside a small membrane or cantilever beam will be operating up and down, so the lifetime is a major concern in MEMS. Mechanical reliability and lifetime is concerned. So please, all of you, look at this advantages and disadvantages of MEMS. The limitation is complexity, fabrication complexity, and initial cost. And one more disadvantage is the lifetime concern. And of course, the third one is speed is limited compared to your solid state devices. But high actuation, high voltage is required to turn it on or turn it off. But as the other parameters are good, insertion loss, isolation is very good compared to other things. Okay, so that is about my MEMS. Yes. Now how I use my MEMS in the how I use my MEMS. In the reflect array. So what do you mean by reflect array? I focus the signal on the array, reflect array. So they are not actually the radiators. They are the antennas. Look at these antennas. They are not active because the signal is not given directly. But I use some antennas to reflect. These patch antennas are meant for reflecting the signal coming from the antenna. So the reflect array, some of them will act as phase shifters. How I use my MEMS to change the phase. So these are the MEMS phase shifters. Okay, maybe 0 or 45, 90 degrees, 135. Okay, based on the direction in which you wanted to change the beam, accordingly, I will control the phase. So it is possible to change the beam from plus 70 to minus 70. So that in the how I control again through MEMS. Yes, now I think this is a beautiful slide. Just look at this. Look at here. Yes. Now I think, are you able to see this slide? Anyone is there online?
Sir, yes, sir, yes, sir.
Okay, ma. Yes. Now look at this structure. There are a number of antennas. Antennas arranged in the form of a matrix. But these antennas are connected through a MEMS switches. MEMS. I can turn them off or I can turn it on. Right? Apply some voltage. I think there are two colors that you are seeing. One is the gold color, the other one is the black color. Black color represents the MEMS switch. The gold color is the patch. Okay. Now look at this. When I use 7x7, this is actually 4. If I use 7x7 antenna, 4 plus 3, 7x7 antenna, and some part I am using as a transformer, lambda by 4 transformer, and feeding. Can you tell me what is the use of lambda by 4 transformer? Those who are teaching EMTL or antennas.
Impedance matching.
Impedance matching. So the major problem in the antennas is impedance matching. My antenna should radiate whatever signal I give it to the antenna. If the antenna impedance and the feed impedance is not matched, what happens? The signal will come back and reflection return loss will be more and the signal will not be radiated. So it is as important as the design of antenna to design the matching. So lambda by 4 transformer will act as a impedance matching between the feeding antenna and the original antenna. So it is a transformer, high to low, low to high. I think those who taught EMTL, they know how a lambda by 4 transformer works, or it will match the line to the load or load to the line. So look at this diagram, S11 characteristics. As I told, S11 characteristics is meant for knowing the frequency of operation. When I use 7x7, look at this, it is operating at 7.5. When I use 7x5, it is operating at some other frequency. It is operating at 15. When I use 7x4, it is operating at 17.5. When I use 7x3, it is operating at 22.5. When I use 7x2, the antenna is operating at 30 gigahertz. Now, what is the thing you are doing? Simply I am turning off some MEMS or turning on some MEMS so that the other patches will become inactive. Only the antennas which are connected to the MEMS are active and will radiate accordingly. Now, what do you understand? Higher the size of the antenna array, lower is the frequency. Lesser is the size of the antenna array or size of the matrix. 7x2 only, na? 7x2 means how many antenna elements are there? There are only 14 elements, but it is operating at 30 gigahertz because the size of the antenna is small. Smaller the size of the antenna, higher is the frequency. Higher is the size of the antenna, lower is the frequency of operation. So all these things are done dynamically simply by controlling the MEMS switches. I am controlling the frequency of operation from 7.5 gigahertz to 30 gigahertz. see the range, how beautiful the concept is, simply by turning on or turning off the MEMS. So you are able to control the frequency. Now, coming to the pin diodes, as I told, yes, pin diode, P-type intrinsic and N-type will be there, and when it is an on condition, the impedance is approximately 0.5 to 3 ohms it offers. When it is off condition, the impedance is about approximately 10 kilo ohms. Yes. Now we have seen how my MEMS switches are used to control the frequency of operation. Now, let us look at pin diodes. Look at this fractal antenna. This is a fractal antenna. Different segments are there. This is a segment 1. This is segment 2, segment 4, segment 1. And look at these diodes, D1, D2, D3. By turning on and turning off these switches, different segments are connected or disconnected so that I can change the frequency of operation. This is a fractal antenna. Okay. But of course, when we use, how do you design, how do you simulate it? Talking is very easy because I can show you the diode, but how do you simulate in the simulation tool? It may be there are different tools available in the market, like our IE3D is there, HFS is there, okay, and CST Micro Studio is there. How do you model these diodes? Yes, this is the way how a diode is modeled. Yes, let me show you a simple example. This is my microstrip antenna. This is a switch. I'm representing this as a switch. I'm not going to show you the actual switch. Instead, I'm putting a path. Okay. When this path is on, the antenna is operating at 2.5 GHz. When this is removed, turned off, the antenna is operating at 2.5 GHz. Okay. Just look at this. Look at this. I think, are you able to see my screen?
Yes, sir.
Sir.
Yeah, someone has written something. I think, can you remove that? I am not able to remove because someone has. Yeah. Okay. Sorry.
I will check, sir. I will check, sir.
Yeah. Let me design the small antenna, and I will show you how the frequency is changed. I'm using one tool, small tool. Yeah. Look at this. This is the substrate height thickness. Let it be 3.2 mm, and the dielectric constant is 2.33, and yes, this is 0.001 is the loss time. These are the substrate materials. Okay, this is substrate materials. Yes, can I hide this? Yes, so I'm using, yes, let me use a rectangular microstrip antenna of size 40 mm by 40 mm. 40 mm by 40 mm. Yes, this is a rectangular antenna, microstrip antenna. Yes. Now, what I do, I wanted to change the configuration of the antenna, and this part of the antenna is connected through a switch. So let me design a small yes, metallic path which will act as a switch. But actually, in reality, we use a pin diode or MEMS. But I am using this small metallic path to connect these paths. Yes, okay. Let me save it. Yes, now let me see at what frequency it operates. it operates don't worry about it. This is the way I'm trying to show you how the frequency can be modified, can be changed by controlling the switch. Yes. Yes, I think you are able to see it is approximately operating at 0.25 and 0.5 it is showing, but it's not perfectly matched. Now let me show you what happens when I remove this one. When I remove this one, yes, the switch is removed. I have removed this one. Again, let me check. Let me run once again. Data, DKH. 1, this is 3, this is approximately 31. Yes, check at what frequency it is operating. Could you recollect at what frequency the previous antenna is operating? Hello? Can you tell me what is the frequency of operation of previous antenna?
0.75, sir.
1.25. 1.25. Previous one is 1.25. Now it is
2.3.
2.3, 2.33, 2.33. Now, what is the changes that I have done? What is the changes that I have done? Only switch. I have not done any modifications. Now the switch is turned off. Previous one is switch is on. So I am able to change the frequency. Okay. So this is the way how we can change the frequency of operation dynamically. Okay, just by controlling the switches. Okay, look at this. Now it is yeah, look at this. This is operating at 2.5 gigahertz. Now when the switch is off, now the switch is not there. Here switch is not there. But now tell me at what frequency it is operating? 2.25. Just turning on or turning off, I'm able to change the frequency from 2.5 to 2.25. Now look at this structure. Look at this structure. This is my antenna. I kept two strips on left and right hand side to change the polarization. Okay. Now when here one switch, the other switch. When both the switches are off condition, now it is giving linear polarization because I use my axial ratio to look at the polarization. If axial ratio is 0 dB, it provides circular polarization. Okay, here look at it is providing approximately 20 decibels. 100% it is a linear polarization. Okay, if an antenna is said to be circularly polarized, the axial ratio should be approximately 0 decibels. Then I can say that it is providing circular polarization. But this antenna is providing linear polarization because current, when I give feeding here, current in the left hand side, right hand side is exactly similar. The current left hand side, right hand side, the path is same, it provides a linear polarization. But look at now let me put this side. I have connected this strip with the antenna. Tell me what happens, the path in which the current flows in the left hand side, the path in which the current flows in the right hand side, is it same? If I give feeding here, look at this, this is my feed point. Can anyone tell? Please, one of you please respond. If I give the feeding here, current flows like this, like this, like this, like this, like this, like this. Right hand side, like this. But this is completely detached from the antenna. So the path in which the current flows on the left hand side from the center is different from the path in which the current flows on the right hand side. So that is the condition which is required to get CP. So now look at this one. I am getting 0 decibels. The axial ratio is 0 decibels. So it is providing circular polarization. Now this is the way how I change the structure of the antenna by controlling the switches. Okay. So I'm getting linear polarization and circular polarization just by controlling the switches. Now tell me, look at this one. What is the difference between this one and the previous one?
So there is no current path on left side, sir.
There is no current flowing in the, of course, current is flowing, but these two are not connected.
Yes, sir.
These two are not connected, but right hand side current path is different. The left hand side current path is different. So to get to circular polarization, we should know the condition. What condition? There should be two modes which should be excited. So TM10 and TM01. TM10, TM01, two modes should be excited only when the current in the left hand and right hand side must be different. Two frequencies must be excited. So that is the reason. Here also I am getting, look at that axial ratio, approximately 0 dB. So here also I am getting circular polarization. So since here it is symmetrical, left hand side, right hand side, current path is same, I am getting linear polarization. In this case, my left hand side current path, right hand side current path is different. I am getting my circular polarization. You should know the philosophy or the phenomena behind for which I get circular polarization. Under what conditions I get CP should be known. Otherwise, you cannot do this reconfigurability. So reconfigurability in the case of frequency or reconfigurability in terms of polarization can be done only what modification should I do in the structure of the antenna so that frequency can be modified. What modification should I do in the structure to get a different polarization? That mechanism should be known to us. Otherwise, we cannot do it. Yes, this is of course my PDA. Now coming to the third solid state device. What is that third solid state device?
Varactor diode.
It's a varactor diode. It's a varactor diode. Very important characteristics of my varactor diode is changing the capacitance by applying the voltage. As you keep on increasing the reverse voltage, what is happening to the capacitance decreases. Okay, na? Simply I am not changing the physical capacitor. I'm changing the biasing voltage. When I change the bias voltage, what is happening? The capacitance changes. But you may be getting a doubt. How my capacitance comes into picture to change the frequency of operation? So you should understand one thing. An antenna, so sorry, all of you, an antenna is basically a parallel resonant circuit. Antenna is basically a parallel resonant circuit. At the frequency of operation, it will resonate. A parallel resonant circuit is nothing but RLC connected in parallel. When a varactor diode, look at this, I have loaded a varactor diode onto the patch, then what happens? This is the way the capacitor is added. Okay, capacitor is added to the my parallel RLC circuit. If I keep on changing the supply voltage, biasing voltage, what happens to the capacitance? Capacitance changes. When capacitance changes, my frequency of operation changes. You know, F0 is equal to 1 by 2 pi root LC. F0 is equal to 1 by 2 pi root LC. Higher the value of capacitance, lesser is the resonant frequency, and vice versa. Now look at these diagrams. For C 3.45 picofarads, yeah, highest C, lowest frequency. lowest frequency, highest frequency of, lowest C value, highest frequency of operation. Now, can you tell me what is the basic difference between the antennas which you have seen earlier and this one? Anyone? There also I changed the frequency. Here also I changed the frequency. What is the fundamental difference? Anyone? Those who are listening carefully, I think they can tell the difference. Okay, I will tell you the difference.
It is resonating at multiple frequencies, no, sir?
Correct, but the thing, multiple frequencies, yeah. Let me come to that point. It is continuous. Yes, where see there at discrete. See, just now we have seen that when the switch is an on condition, it operates one frequency. When switch is an off condition, it is operating one frequency. 2.25 and 2.5. In between those 2.5 and 2.5, I don't have any other frequency. But here, by changing the biasing voltage, maybe 0.1, 0.2, 0.3, 0.4, continuously if I change the biasing voltage, the capacitance also continuously changes. The frequency of operation also can be changed continuously. A continuous frequency change is possible with the varactor diode based frequency reconfigurable antenna. Suppose I have 2.45 gigahertz. You wanted to make the antenna to operate at 2.46 gigahertz. It is possible. Appropriately change the biasing voltage. Appropriately the capacitance will change. Appropriately the frequency of operation can be changed. So continuous change is possible with the help of varactor diode because by changing the biasing voltage, capacitance can be changed appropriately and frequency of operation. So this is also a wonderful solid state device which is generally people use to change the frequency. Yes. Now coming to the liquid metal, we are talking about this condition of the structure of the antenna. But here I am trying to change the material characteristics. I am injecting some liquid metal. Liquid metal, when I am injecting into the antenna structure, the frequency of operation can be changed, pattern can be changed, or the polarization can be changed, depending upon the type of the material. Depending upon the type of the material, or phase change materials are there. Okay, phase change materials are there, or the frequency variable metals are there. Liquid metals, we need to inject liquid metal tuning for polarization, radiation pattern agility is possible. Phase change materials are also there. How do you change the phase materials? Optically controlled. Okay, so here what we do in the liquid metals, what are those liquid metals? Like gallium based alloys are electrically conductive and can change the shape when injected, retracted, or moved inside a microfluidic channels. So I will inject some, what do you call, into the structure of the antenna so that this shape or the electrical conductivity can be changed so that I can change the frequency of operation or the polarization or the pattern. This is a wonderful concept which can be used to change the frequency or polarization or pattern. Now look at this. How we change the pattern through mechanically. Yes, mechanical. Look at this. This is a structure. This is a motor I use. I rotate it. When I rotate it, what happens? The direction of the radiation pattern can be changed. The radiation pattern direction can be changed. Of course, this is a mechanical way out. But in the case of optical configuration, I use some materials like PCM. PCM stands for phase change materials. When light falls on it, the phase of that material will be changed, so that the current given to an antenna phase will be changed, so that the pattern can be changed. That is optical excitation. Yes. Now we are talking about the antennas, how we change the structure. But tell me, what are the basic structure of a microstrip antenna? Can you tell me, anyone? Those who worked on microstrip antennas? What will be their bottom side? Bottom side? what
The
will be there?
bottom is ground, sir.
Yeah, bottom is ground, substrate and patch. Am I correct?
Yes, sir.
But we are talking about only the structure of the antenna, patch antenna structure. How do we change? But we were not talking about the substrate. Okay, even the frequency of operation can also be changed by changing the properties of the substrate, like flexible. Look at this. The flexible substrates are there. Rigid substrates are there. I can use MEMS as bridge materials. Okay, so this is another way of changing the frequency, not through structure of my patch, even by changing the substrate materials characteristics. Also, the frequency can be changed. Substrate materials impact on reconfigurable antennas. You might have heard about the wearable antennas, textile antennas. So even on our pant also, antenna can be printed. What is the substrate for my pant? Jeans. Jeans is a substrate. Okay. So by changing the material, which I use as a substrate, by changing the properties of that substrate, like epsilon r can be changed. Epsilon r 2.2 to 4.5, I can change. Because if you look at the frequency of operation, my epsilon r also comes into picture. Those who work on the microstrip antennas, you know that frequency of operation is related to the epsilon r, dielectric constant. So if I change the dielectric constant, can't I change the frequency of operation? Can't you change the frequency of operation by changing the epsilon r or the properties of the substrate? Yes, we can do it. Yes. Now, of course, okay, we talked about all these things, but what is the thing which we need to understand is biasing. Biasing is actually DC. My antenna is RF signal, but there should not be any interference between this. Okay, we have to be very, very careful to block this DC, especially for the RF signal. So this is my antenna element. This is a switch. This is a feed point. Okay, so then we should block, especially when the signal is given to the antenna element, because for biasing we need DC. For antenna, I use I need RF signal. Okay, so we should see that they are isolated. RF isolation technique must be used. There should not be any interference between the my RF signal and the DC bias. Yes. Now coming to everything is okay, but how do you do this one? How do you bring out a model antenna? Yes, I use a CAD design for designing the structure. Then I use my EM solvers. What are the? Can you tell me what are the commercially available simulation softwares like HFSS, CST, FICO? Okay. Then what are the results that we have shown? S parameters. Just now we have seen S1 characteristics, return loss characteristics, patterns. These are the results. Then do you think that whatever method that I follow to design is optimal? No. I use my machine learning optimization techniques. These results obtained from the CM solver, I use my machine learning optimization techniques. Even HFS is also having built-in optimizers are there. Now your machine learning optimization techniques can be used to optimize results. Again change it, again EM solver, again results, and check. Now people are talking about the digital twins. Have heard about digital twins? Everyone cheptara? Can you tell me what is actually digital twin? Digital twin. Digital twin, anyone? What do you mean by digital twin? I am trying to replicate the digital replica of the physical one. So you have an antenna, let us assume you have an antenna, physical antenna is there. I wanted to have the exact replica, digital replica of the physical one. Yes, it is possible. You have, let us assume one object is there, You wanted to have exact replica of that. It is possible. We call it as a digital twin. Twin means two, na? Digital we are replicating. So that is to get the actual model. Okay. So this is the how we model, how do we simulate it. So you should know how to use those simulation softwares like HFSS, CST, and FICO. Okay, so what are the parameters that we see? S parameters and pattern. Then we use optimization techniques like any machine learning optimization techniques, neural networks, genetic algorithms. Okay, na? So those things I think will be covered in the next by the next speakers. Yes, this is the external validation. After we bring out the antenna model, what we do? Yes, we fabricate it. The antenna should be fabricated using photolithography technique, and we test it. Once the antenna is designed, fabricated, is it over? We should be tested. Can you tell me one instrument which we use for measuring the ATAL loss characteristics or S1M characteristics? What is the instrument that we use for measuring the S1M characteristics or ATAL loss characteristics?
Vector network analyzer, sir.
But yes, we call it as a VNA. VNA is a vector network analyzer. And what is the thing that we use for measuring the radiation pattern? Chamber, anechoic chamber. Okay, na? So this is a process. First one is we simulate, we design, and we fabricate, and we test it. Okay, so how do you measure it? Yes, vector network analyzer, chamber, of course, probe for compensation, and the power meter. So these are the different methodology flow that we follow to bring out actual model. Nowadays, people are using 3D printing also to bring out actual microchip pattern. Of course, the same concept is used in the pin diodes. Yes, yes. Now look at this. Let me take two more minutes. Yes. Now look at this. How the polarization can be reconfigured using liquid metal. Yes, there is a slot, C-shaped slot on the patch. By injecting, this is the inlet 1, this is the inlet 2. I'll be injecting the liquid metal into the slot, either this side, from this side, or this side, so that the polarization can be reconfigured. When no liquid, then it operates in the linear polarization. When it is injected from this side, left hand circular polarization. When it is injected from this side, other side. Look at this. Default state, linear polarization. When no liquid is injected into the slot, I am talking about liquid metal. Okay, na? If I inject some liquid into the structure, the polarization can be changed. If I don't inject anything, default state, which polarization the antenna gives? Linear. If I inject right quadrant from this side, it's right hand polarization. If I inject from the other side, it gives left hand circular polarization. So polarization reconfigurability can be done through liquid metal injecting into the structure. Okay. Now look at the comparison of RF MEMS, pin diodes, varactor diodes. Okay. RF MEMS best feature is best isolation is excellent, but pin diodes isolation is good. But whereas varactor diodes are considered, tuning is continuous. Continuous tuning is possible. But RF MEMS low loss, lifetime is limited because it's a mechanical connection. But pin diodes, loss is moderate, linearity is poor. But whereas varactor diode is concerned, range is limited because I cannot change the capacitance over a long range. So the capacitance of the varactor diode can be changed over a limited range. So range of frequency over which the frequency of operation can be changed is limited in the case of varactor diode. Okay, but we have to be very careful since the structure is there in the antenna, but we should see that interference is not there and matching is possible. So because when it is changed from one state to the other state, what is the guarantee that the antenna is perfectly matched? So that is to be taken care of. Yes, now look at this frequency taken. Of course, some more case studies are considered. There are 3 diodes kept over here, and how the frequency is changed, how the polarization is changed. how the pattern is changed by changing the structure. Okay. Of course, we can use AI-driven antennas for optimization. That is, of course, that is not my point of discussion. You can combine all these things, whatever we spoke about, like frequency, pattern, and polarization, can be combined like this through electrical, optical. Okay, I use PCM optical layers. PCM means phase shift, phase change materials. I can use MEMS. I can use mechanical control so that hybrid reconfigurable antennas can be possible. It is possible to change the frequency. It is possible to change the pattern. It is also possible to change the polarization in single antenna. This is multi-parameter tuning. Okay. Yes. Now this is the comparison of whatever devices we have seen. Okay, based on the requirement, based on the cost, and we should choose an appropriate method to reconfigure the antennas to change the frequency, polarization, or the pattern. Each one is having its own advantages and disadvantages. Look at the RF MEMS. It's low loss, high isolation, but complexity is more. Look at pin diodes, fast switching to low cost, but non-linear, but it generates heat. Look at the varactor diode. Continuous control is possible, but no mechanical parts. What is the disadvantage of varactor diode? Limited range. Biasing is very difficult. Liquid metal, unique polarization, that is a unique feature. Flexible geometries, but mechanical handling, slower response. Then as soon as I inject the fluid, you don't see the response immediately. Optical, high frequency of operation. No electrical bias is required, but complexity, control complexity is very difficult. Integration complexity is also more because light comes into picture. But finally, metamaterials. Metamaterials are the different materials whose epsilon r is in the negative range, I think, which is not available in real time. Even reconfigurable antennas can also be used in the MIMO antennas. MIMO antennas, one problem within the communication is the fading. Can you tell me how do you avoid fading? Those who are teaching the communications, can you tell me what is meant by fading? Anyone? Fading, what is meant by fading and how do you avoid fading?
Diversity techniques using, sir.
Yes, using diversity techniques, you can avoid the fading. So diversity, frequency diversity is there, phase diversity is there, polarization diversity is there. Here, I can use my reconfigurable antennas, MIMO is like a multiple input, multiple output systems. Okay, these things can be reconfigured. MIMO antennas are especially used to address fading. Okay. Yes, this is the way I measure the radiation pattern. This is an anechoic chamber, where the reflections are completely absorbed. When I measure the radiation pattern, the observers, these are the observers, they will not reflect the signal back. They absorb completely. If they reflect, I think the performance of the antenna is affected. Okay. Now look at this for the final thing. Pin diodes, varactors, RF MEMS, and liquid metal. Okay, so I think you can see the performance is high for liquid metal, performance is low for the pin diode, but manufacturing cost is high for this liquid metal. So this is the conclusion. Reconfigurable antennas are crucial for future adaptive wireless systems. Switching techniques like RF MEMS, pin diodes, varactor diodes, definitely they can use them for controlling the frequency. But the challenges remain integration. How do you integrate into the devices is a challenge. Biasing is a challenge. Stability is a challenge. But advanced materials and AI-driven design hold promise for the next generation smart antennas. Okay. But future research is how do you integrate AI into the antennas? How do you integrate these controlled antennas into 6G systems, energy harvesting, quantum switching, and digital things? These are the future research directions as far as the controlled antennas are concerned. That's all from my side. Thank you.
Thank you, sir. Thank you for your informative session. I
Any
hope your
question?
talk. Yes, sir. Yes, sir. Please continue.
Yes, proceed, Imran.
Any queries from the participants, please?
Hello, good evening, sir.
Yeah,
Sir, my name is Ahmad Basha, sir.
Ahmad Basha. Okay, tell me, Ahmad Basha.
Sir, can we use these reconfigurable antennas for quantum computing, sir?
Yes, but the switch is very. If the quantum computing is high speed, not very high speed. Am I correct?
Yes. Yes, sir.
When I go for high speed, let us think of the switches which we use, like pin diodes, MEMS, or the baractor diodes, whether they are in a position to respond for the fast changes. That is important, na?
Yes, sir.
That if those devices which are using as switches, if they are able to respond for that much speed, we can use. But I doubt those switches are able to operate at that high frequency. It's a question mark.
Okay.
Because the limited switching speed is a big question mark for quantum computing.
Okay, sir. Thank you, sir.
Okay, sir. We'll wind up the first session here.
Okay, thank you, Brian.
Thank you, sir. Your talk has provided us deep insights in antenna technologies and practical design considerations, sir. I hope all the participants have greatly benefited from his expertise. Sir, once again, on behalf of organizing committee, all the participants, I extend my heartfelt gratitude to you, sir. Thank you for sparing your valuable time and sparing your knowledge with us. Now, this is the time for session 2. I shared feedback link in the chat box. Whoever attended for session 1, please fill it. In a couple of minutes, session 2 will begin. The resource person for session 2 is also ready. Now, the feedback link is shared in the chat box. Please fill the participants. So, thank you, sir. Sir. Morning, sir. Session. Sir, thank you. ఉన్నా సార్ చెప్పాను మీరు ఒక క్వశ్చన్ అడిగితే ఆన్సర్ కూడా ఇచ్చాను థ్యాంక్ యూ సార్ పీపీటీ షేర్ చేయండి సార్ వాట్సాప్ థ్యాంక్ యూ Dear participants, feedback is mandatory to mark your attendance. I request everyone to fill the feedback. Okay, dear participants, now it is the time to start the session 2. Now we also have the distinguished resource person in the room. It is my privilege to introduce our distinguished resource person for the second session. He is Dr. S. Kranti Kumar Garu. He is an accomplished academician and researcher in the field of computer science and engineering with over 18 years of experience. Now, he is the associate professor and head of the department of CSC AIML course at Symbiosis Institute of Hyderabad, Symbiosis International Deemed University. He completed his doctorate in quantum computing in allied cryptography from Geetham Deemed University. Alongside the academia, he brings valuable industry experience also. He worked as data specialist at IBM India, where he contributed to expertise, great data warehousing, and analytics platforms for TIAA-CREF. On the research side, Dr. S. Krantikumar Garu has made remarkable contributions. He has authored more than 35 research papers in all the reputed Q1, Q2 SCI journals. He is also an editor-in-chief at the Center of Cyber Security, Center of Science, which are leading open access journals. He has also co-authored a book titled Quantum Computing Models for Cybersecurity and Wireless Communications, which is published by Willy Savenir. In addition to this, he has published 12 patents covering diverse applications such as predictive maintenance for IoT, AI-based cyber attack detection system. Dr. S. Krantikumar Garu has also served as keynote speaker, reviewer, technical chair, and mentor in several national and international conferences. He is also a senior member of IEEE and a lifetime member of IST and CSI. On behalf of Department of EC and all the participants, I extend a warm welcome to Dr. S. Krantikumar Garu. Now I invite him to take over this session. Krantikumar sir, please.
Yes, sir. Sir, do you hear me? My voice is audible to you? All the participants?
Yes, sir. Yes, sir.
Do you,
It is audible, sir.
yes, sir. Thank you very much, Imran, sir, for your kind words, and thanks for the opportunity. And I appreciate all the management and followed by the coordinators for this program. And as sir said that, I am more into some quantum cryptography, quantum key management, and something related to cyber security and quantum machine learning concepts. And today we are handling about how these artificial intelligence and followed by IoT systems and antennas beaming together for better sustainability, for better improvement of the societal problems. We have a multiple sustainable development goals are there. So the main purpose is so um, here artificial intelligence basically that is primarily enhances the capacities or capabilities of Internet of Things. I can say that in our childhood onwards, maybe in the class 12th or BTech first year, second year, we talk about what is hardware, what is software. When we are go with that primary level of what we called IT information technology lab, they talk about what is software, what is hardware. So how these two things are combined with each other. So when I talk about, I try to relate here, artificial intelligence is something like a software to do some better applications. And in case of IoT, I can say that it is something like a hardware to execute those multiple applications of artificial intelligence. And I'm sharing my screen. Just a minute, sir. Are you able to see my screen?
Yes, yes, sir. It is visible now.
Yes, yes. Right. So today we talk about something related to AI-driven smart IoT and antenna systems, and followed by what are the different types of real-time applications possible with respect to different types. In what way these three combinations will help you for a manufacturing team, or followed by agriculture team, or some resource management, water management, those things. So here, the main purpose of the combination of artificial intelligence and information of technology. So it is about in what way these two are combined with each other, and the transformative potential of AI lies in this ability to empower the specific set of IoT devices with analytical capabilities. So here, analytical capability means in what way IoT devices are extracting those data. Whatever the data we received, on top of the data, how can we generate some analytics to generate some set of reports? Based on the reports, we can go with the advanced statements, and how can we compare with the previously available results and present results, and based on the comparison only we can decide what type of changes we need to take over for the better improvements. So here, the main purpose is the Internet of Things facilitates data collection and connectivity for a wide range of applications, connecting such as we call it as a physical devices, or such as vehicles, uh, smart devices or apartments and other objects through sensors, antennas, softwares, and network connectivity. So this interconnection, that is combination of IoT and AI, that combines, which allows for the exchange of data and enables remote monitoring and control, forming the backbone of numerous smart systems. So the integration of AI and IoT enables automation and real-time monitoring in diverse environments, such as transforming industries and improving the quality of life. By combining the data collection capabilities of IoT with the analytical power of AI. So I mentioned 2 points: data collection capabilities and analytical power of artificial intelligence. These two are best combination. So because IoT, they are not static, sometimes we can combine with multiple systems, and based on the availability, and again we diversify the different combinations when multiple IoT devices are communicating with each other. So whatever the data is transmitting, so those data we collected and we stored, and on top of data we generate some applications, we apply some artificial intelligence algorithms to get some beautiful analytics. So that systems can respond dynamically to changing conditions and optimize their operators, leading to enhanced productivity and sustainability. So here, the specific machine learning concepts integration with AI and IoT in urban settings enables real-time data collection and predictive analytics, addressing the challenges of modern cities through these intelligence insights. This integration supports the development of smart traffic management examples also, and energy efficient buildings also, and predictive maintenance of infrastructure, improving the overall livability and sustainability of urban environments. So there are multiple points out there. So here I provide some sample in what way these combinations worked out. So technology convergence, it is talking about in what way these IoT, artificial intelligence, and different types of networks are maturing simultaneously, are improving simultaneously, and this combination allows real-time sensing with respect with the help of IoT, and rapid learning by using artificial intelligence, and ultra-fast communication. We call it about 5G or 6G now. Now 6G not into exact coming to the picture, still 5G is working on that one. So for example, smart agriculture sensors, I can relate with these things. So data transmission via antennas, data transmission that is a part of IoT devices, and a subset of AI models in the cloud or edge computing, that immediate actionable decisions. That is called, we can dynamically take the decisions depend upon the existing conditions or situations. So second concept, right side, we talk about a decentralized intelligence. So decentralizing means, centralizing means we store all the data in a particular point of time, and everybody try to access the data from that point. For example, we are maintaining a common data center in one particular point, and multiple organizations extracting data from that particular point. If sometimes if it damages, so there is no choice of backup. It is not possible to extract the data. So at that time, what we do is based on the availability, we based on the requirement of specific zone, you just make a copy with yourself. That is, instead of centralizing all intelligence in the cloud, we can combine artificial intelligence with IoT, pushes intelligence to the edge. Availability of when at that particular device is available, we can access the data from that particular edge. So which benefits includes low latency, reduced bandwidth consumption, high privacy, and faster decision making. Here, high privacy means in that particular zone, we have a full control over the data which is you belongs to, because we are not maintaining centralized things, right? For example, a wearable, we can say that many people are using smartwatches. So a particular smartwatch that direct or detects irregular heartbeats locally without writing or waiting for the cloud processing, right? We are maintaining our own individual storage, and we are maintaining and that particular watch or thing that is only extracting algorithm content only from the cloud. And while it is running, automatically we can take the decisions, because when we want to wait for the decision from the central device, it may take more latency. It will take more time to send the signal and to revert back the signal. It will take more time. That way, we are not supporting to work with centralized. So we supposed to go with the decentralized facility. And that next one is the data explosion. With the billions of IoT endpoints or devices, data is exploding at almost 85% CAGR, because based on the report in between 2017 to 2025, as far as my knowledge is concerned. So for this one, AI is important or essential to process this massive data in real time, right? So antenna systems are equally critical. They must handle high throughput and spectrum efficiency and adaptive beam forming to keep up. That is something about this one. And next one is new design mindsets. That is, traditional systems capture data passively, because there is no chance of extracting data actively based on the real time, because when we change the location, we come up with the multiple common. When we are moving from one place to other place with respective devices, it can access nearby devices, and at that time, whatever the data we stored in the previous way, it is not possible to available. So every time we need to change that one. That is, these artificial IoT systems are designed for intelligence from the ground up. And for example, AI-driven irrigation systems, that is a crop system that not only sends soil moisture, but also predict drought impact and autonomously adjust water schedules based on these reports, right? And here, this is one of the how many number of industrial connections with respect to IoT in between 2018 to 2028. So here I'm reporting in terms of billions only. So here they talk about, uh, according to the reports of Statista, they said that almost 4.37 billion industrial devices will be connected to IoT technology. So for to handle such huge data, it is not possible to maintain. Or for example, a simple thing, we have 1,000 records in a particular system. We can use some different types of searching algorithm passively. So it sets by line, or point by point. So it will take more time, but we need some automation, artificial intelligence algorithms that will uh, rapidly extracting or searching data from the IoT, and they can report with the minimum time complexity, minimum space complexity. That is the point here. So we mentioned in that, based on the report, we are almost that much content. We have that one. So to handle those things, it must to work with artificial intelligence and machine learning for the automation process and for efficient execution of the problems. So this is one of the example of evolution of antenna technologies in between 2000 to beyond 2024. So here, let's talk about this one, the evolution of antenna technologies over the past 2 decades, and see how they have transformed our communication systems and applications. For example, if you consider early 2000s, these are the simplest antennas, the basic building blocks of wireless communication. They maybe work for different, that some different computer network protocols. So the main applications were, that RFID systems, for example, we provided some of the tags for shopping by scanning through mail or ID cards. This was the first step in connecting physical objects wirelessly to extracting data. Now we move to the next phase, 2005 to 2010. It is something like we use some chip called microstrip patch antennas. This became smaller and flatter, leading to microstrip patch antennas. These were widely used in what we call as now we are using Wi-Fi routers only. In the Wi-Fi routers, these people are using that one. This period marked the growth of wireless internet at homes and offices. As of now, we are using the same thing, and we are continuously evolution from that basic version to modern versions also. Now, if you look into this 2010 to 2015, to meet up the demand for faster mobile data with respect to we talk about 3G, 4G, 5G. So we use multiple input, multiple output antennas were developed. They allowed basically some 3G, 4G, LTE networks to deliver high-speed internet to suffice the user requirements. And for example, we talk about in when we are in 2G or 3G, when we call about video streaming, at that time it was very slow, and those cells are so very distracting, and we are not able to buffering is also very difficult. But because of these MIMO, multiple input multiple output antenna concepts, video streaming and mobile internet truly become possible at scale level. That's what I can justify with this application. Now we talk about 2015 to 2018. That is beamforming antennas. Still, people are using the same thing. So that came beamforming technology where antennas could focus a specific signals in specific directions rather than spreading them everywhere. They can streamline in a particular way. This supported smart city infrastructure such as smart traffic lights, surveillance, and public Wi-Fi. In public Wi-Fi also, we can create multiple access policies. And even though in our institutions, in our universities also, we can create a particular Wi-Fi network which is dedicated to students only or faculty only. For faculty, we can provide, maybe they are having some good research and development works. We can enable 1,000 GB also. We can enable them. For student, a limited amount of these also. So these supported beamforming gave us efficiency and reduced interference also. And we moved to 2018 to 2020. Now we moved from in this band, we moved from 4G to 5G. So they talk about this a big revolution. Now people are using the same thing. That 5G antenna using I forget about that name. Some microwaves and millimeter waves that enabled very high speed, ultra low latency communication, right? And some of based on those 5G, because based on the user applications only, we can perform those things. So there in 5G, we can include industrial IoT and the smart factories, and we can do with some robotic automations and real-time control also. So in 2020 to 22, they talk about wearable antennas. Antenna become flexible and wearable. So it's something what we are using in smart factories and also in health monitoring devices, smartwatches, and some of the applications. I can say that a worker safety suit with embedded sensors transmitting data in real time, right? So when we are working, for example, people are working in some what we called biotechnology labs, when they're working in some hospitals, when they're working in some coal mines. So based on the heat, they sensor automatically, and when the threshold level is crossed more than high, it beams some alarm, so that they can do some precaution activities. That is something about that wearable antennas. And from 2022 to 24, that is we call it as something here. We are combining some AI techniques also. We call it as uh, reconfigurable uh, some intelligent services, RIS. I don't know about the full format that one. So these antennas are now becoming smart environments. This particular technology can redirect and control radio signals very smartly or intelligently. So one suitable application for this one is environmental monitoring, helping track pollution, water quality, and smart agriculture. It is very helpful to those things also. And finally, beyond that one, 2024 and beyond, now we are in 2025. Here we combine that adaptive antennas with respect to AI. So here we can easily combine, that is the compatible hardware software combinations where we design such antennas which is compatible to they listen, they can work with AI algorithms for future. They can learn, adopt, and self-optimization in real time without manual intervention. Once you train that particular data, and we can give it to that particular AI-driven antenna systems, So automatically, when the next time the same scenarios will come, they automatically machine learning that one and will take their own decisions. And there we can reduce the manual intervention because we don't know at what time what will happen. So these things are specifically related to IoT in healthcare. For example, wearable sensors sending health data securely and efficiently to doctors. For example, I can say that some people are having in critical sections. Maybe some heart patients are there, some neuron damaged patients are there. At that time, they can put some wearable devices. Automatically, it reads the data from there. Whatever the data it is reading, it's showing directly onto the doctor app. We maintain a common doctor app. So when that signals with respect to brain signals or heart signals, when it is crossed to a threshold value, automatically it alerts the doctor so that they can take effective treatment within the described time or limited time to avoid the loss of life. That way you can help out those things, right? So this entire this evolution of antenna technology. So antennas have evolved from simple metal rods in way back to 2000s to intelligent AI-driven systems up to beyond 2024. So each stage was not just a technological improvement, but also a foundational for the next revolution. Because based on the user requirements, based on the demand, we need to upgrade, right, based on necessity. So here we talk about this one. So here I mentioned some reconfigurable IoT antenna systems. So these are some critical components with respect to IoT devices and adapted to AI networks, AI algorithms also. So here I provide a sample diagram, a schematic of reconfigurable IoT antennas. So here we showed some ground key components, that radiating element. This is the actual part of the antenna which is responsible for emitting and receiving electromagnetic signals. Maybe most of these people may be familiar with that one. So I'm learning these things because I am not, I have a different set of area. But here in this section, I try to relate these things with some demonstration also. I performed some of the sample toy algorithms by using Anaconda distribution and Jupyter notebooks. And once it is completed, I try to demonstrate by taking a simulated 5 different nodes and how those two are communicating with each other with respect. Without A, what will be the scenario? With A, what will be the scenario? So for that, some people may not be familiar with them. So that's why I'm projecting this one. So here, frequency switching module that usually made from different components, tuning components such as pin diodes or varactors and control circuit, microcontroller. I'm not that much things about these things. So, but the main working is the microcontroller interprets the desired communication configuration, and it can possible to send the signals to the control circuit. So the control circuit activates specific switches in what way in the frequency switching module. So by adjusting the different set of modes, the antenna can transmit, receive on various frequency bands or alter its radiation patterns. So this is something about the role of antenna systems in IoT. Based on the frequency, we can capture the data, we can store the data, and whatever the data we store, we can transfer that particular data to further analytics by AI. That is coming to the next slide. So here we talk about the as of now we talk about what is the role of what is AI, what is IoT, what is antenna systems, and how those combine. If combine those three, what will be the advantages? So here I can go with this smart environmental monitoring system with the combination of AI, which can optimize. Just in previous slide we talked about antennas are able to capture the specific frequencies we can send and receive. So we can receive the particular data with threshold level 1, level 2, level 3, level 4. So based on that one, these AI algorithms can extract the data, which is a part of IoT devices, enabling real-time adjustments to maximize the signal strength and minimize the interference. So here I can provide a sample picture in what way these smart environments monitoring and optimizing the data in real time with the combination of AI and followed by that IoT. It is a part of the combination. Antenna is also a part of those things. Now here This is I try to relate with a specific AI-driven smart IoT systems with respect to agricultural and variables. So if you look into this particular diagram, I extracted this diagram from a particular research article I cited in the end of the PPT. So here, this IoT enabled agriculture, that is if you look into that one at the bottom left and top right corners, you can see IoT agricultural lands equipped with sensors, multiple sensors. Sensors means soil sensor, moisturizing, heat, many things are there. That is different scenario. So these combination of sensors, they can measure environmental conditions such as soil moisture, or what is the temperature and what is the humidity, and for which particular crop, which land soil is suitable. And these AI algorithms process this data, whatever the data were extracted, that is the data related to temperature, the data related to soil moisture, or the data related to humidity. So these AI algorithms process data to provide predictive insights for precision farming. So here the point, precision farming is very important. That means based on the soil moisture, before we are taking into consideration, we have a concrete evidences that this particular uh, uh, type is very suitable to that particular soil. So that if you inform the same thing to farmers, they will be benefited based on whatever the things we are giving the data. And next, smart sensors and monitoring devices. So, as I already said, that multiple sensors are there. That is the with depicted with thermometer or a droplet or other icons. Here I shown that one. So they are continuously collecting environmental and biological data based on the some season to season, and the day and night they're continuously capture the data. Whatever the data they are captured, we are extracting to decentralized environment, and that data ranges from as I said, the climatical conditions or soil metrics or crop growth patterns to wearable biometrics. I can say that smartwatches, right? So smartwatches play a vital role, that they represent how that human-centric IoT applications, that is health monitoring or stress tracking or physical activity analysis. It is apart from that particular these things, and with AI integration, these devices can predict different types of anomalies also, and signal propagation, that in that figure I show that different types of dotted signal. These desired lines are labeled signal paths, illustrate how data flows across those multiple devices and multiple and antennas and devices, and how the way, for example, if you look into the radmark and sensor, it captures the moisture rate and send it to some other nearby thing. Through that one, we can receive the data. In home also, we can extract the data, you can monitor it. Like here, it's in case of I show that A integration also. There, A plays multiple components are there. First thing, it is analyze the data, extracting actionable insight from raw data, and sensors, some variable data. From that, it is network optimization, managing antenna beamforming, spectrum usage, and signal routing for efficiency. Next, real-world application supporting, as I this slide show that here, for example, I can mention smart agriculture. We can extend the same thing with wearable health monitoring or sustainable IoT ecosystem. So finally, the figure demonstrates a convergence of IoT sensors, wearable devices, and antenna systems, all coordinated by AO by doing some automation process, by trying the data, analyze the data, pre-process the data. Such integration enables real-time decisions making very quickly in different domains. Here I'm talking about agriculture, healthcare, and spot environment zone. So antennas act as a communication enablers, with AI ensures intelligent connectivity and data-driven automation. So here I mentioned one more point, that is called the spot environment monitoring and analytics. Of course, as of now, we talk about the same thing. In what way we can do the environment analytics and everything. And the next point is here in specific, in previous up to 2024, we talked about 5G communications. Now most of the research works are happening in these 6G networks, and in what way they're communicating with each other with the smart home devices, simulation platforms, and everything. Even multinational companies also working on the same work. Once they got some stabilized network, they come into the picture in the real time and the prototype designs. So in this picture, I try to mention that in what way these 6G antenna array, that is the orange and blue grid represents the antenna array. The purpose of this antenna arrays are used to advance wireless communication to generate and direct and manage signals. As compared to 5G with the advanced, theoretically, as of now, people are talking about that one. But some of the research works have happened, but and large level, we are not able to see. We need to see. We need to wait for those things also. So this is something about this diagram about 6G network. Something about uh, in what way we can establish the communications and those physical and digital worlds. So let's see. I can go with some sample algorithms, and it is not possible to type all the code now. Here, I come up with one particular AI model. I didn't take most of the AI models, so I take some random forest regression classifiers. Um, we can train this one for the predictive optimal antenna beam, select beamwidth, and enhanced network. And for this one, I can. So if those who are working in this particular area, so this is a right session. So I already installed this. You can go with Anaconda download. I can share with you by using code also. So what is chat box? So you can download that particular Anaconda distribution if you're necessary. So we can download here. Once it is completed, there is a Anaconda PowerShell prompt. Are you able to see my screen? My voice is audible to you, right? Okay. Okay. Yeah. Thank you. Yeah. Thank you. Thank you. So now I open this PowerShell prompt. Okay. To maximize. So here I already installed this Jupyter notebook also. It will take some time. Have a low bandwidth here. Yes, it is already installed. It is opening. So the main purpose here, I try to. It's not about a real-time data, but in what way these IoT, AI, and these antenna systems are combined with each other. So in this basic demonstration, a synthetic data representing IoT node, a simulated node, positions in polar coordinates, that is we call it as a distance and followed by angle, is used to train an AI model. In our example, we talk about random forest regressor to predict the optimal antenna beam direction. That goal is to point the antenna toward clusters of nearby IoT devices to extract the data and to imitate them how smart antennas dynamically align beams to optimize communication. This is a direct reflection. And for that one, it will take some time. So, anyways, I'll share this code to you for the demonstration only because a theory session, I'm not able to spend that much time on theory. So for this one, I installed these NumPy and everything. So here, I do one thing. I just copy this one. I just open a new. Sorry, new Python. Right. So here, I'm not talking about any code here. What I did is, in the context of this AI, IoT, and antenna systems, in modern IoT networks, we deploy thousands of small devices because I already explained those things are sensor, wearable devices, industrial nodes, many things are there that communicating wirelessly. So the main challenges are efficient spectrum utilization, efficient utilization of signals, and reliable connectivity, which is secure and which is not tampered. And with respect to energy efficiency for low power IoT devices, because the energy consumption is very important here to manage optimization important, and the adaptive or dynamic beamforming to focus signals where needed. So this is where AI-driven antenna control becomes a crucial role. So here, in second point, we talk about antenna beamforming and IoT nodes. Imagine an IoT hub like a base station at the center. Around it, multiple IoT devices, we call it as a nodes, are scattered randomly. To communicate to all those IoT devices from this particular base station efficiently, the antenna should focus its beam toward the region where important nodes are located. But instead of manually tuning, we use AI. That's all. As of now, we talk about manual intervention. But when the number of devices are increasing or coming to the network, it is not possible to maintain physical manual intervention. That's why we come up with these AI models to lend these beam direct automatically. So here we talk about this one. This is the highlight point. Here I just take this particular minimum nodes of 5. So here the generate nodes, that particular function, that function simulates IoT devices randomly placed in specific places with some regular distances. Here the point of node futures. This particular node futures usages converts a device positions into structured input, a combination of X and Y or different types of coordinates, as I mentioned about in the previous section. Uh, the main point is this is similar to how a base station senses the distribution of the IoT devices. See, I try to, it's a toy example only. In case of generate nodes, I talk about 5 nodes with that random uniform function. It can locate anywhere, any combination. The future of the second section is it is about to identify the, I mean to say that with respect to base station, it need to senses that one. And next, this particular function, what I mentioned, this particular function. So this is about computed target vectors. The main point is it calculates the best beam direction by giving more importance to nearby nodes. In terms of how I believe that you know about that signal to noise ratio, basic formula is there. Need more priority, and closer nodes having that SNR ratio, and farther nodes lower SNR ratio. That is signal to noise ratio. For closer nodes, it is more. We need to capture those things. So last one, that vector to angle, that converts the beam direction into an angle, which is exactly how antennas treat their beams. So it is not actual data. I try in the previous slides, I explained about what is antenna, what is sensors, how these multiple devices work with base stations. I need to project the same replica with a sample program. And finally, that code is basically a mathematical, a toy model for adaptive beamforming. So here, finally, we store all the data. And next, we go with this one, second set. So here the assumption is I take some sample sets. Here I try to, in previous code snippet, we take up one particular base station and we generate some 5 to 6 IoT nodes. Now, in what way AI model preparing training data or train a small random forest regressor here, That is called here in IoT networks, no distribution is dynamic, because all of you know that one. Devices join, leave, move, things are happen dynamically. So we cannot hardcode beam directions. Instead, we create a synthetic data set, because in real time I tried, but this Google Colab I'm not able to spend. That is not worked out. So here I talk about two things are there, X and Y. Here I highlight those 2 points. This vector X is assumption is IoT node positions with angle and directions, and this output Y is computed best beam direction, because base station, and if you have a signal to noise ratio is more, it is nearby. So we need to change the direction to that particular point, that particular direction. So computed base beam directions using a weighted rule. So here, this data set is like some simulation lab data where a lens before being deployed, right? So here, why I specifically random forest means it is assemble ML method, and we have a predefined functions available in Python. It builds multiple decision trees and average them, because it is robust, handles non-linear relationships also, and maybe it requires a little parameter tuning. Anyways, we can see that. So most probably it can suitable for multiple output regression. In our example, we talk about X and Y components of the beam vector. So in this context, the model learns the mapping from IoT node distribution, optimal antenna. So IoT node distribution we already completed in before this session, before this one here in line one. In the snippet of code, we done with that IoT node distribution. And in the second snippet, we talk about training. And next, we go to, if we look into this one, see here, are able to see this one? So some generating data set training model by using that regression, random forest regression. We train random forest regression. It is training is completed. And next, go to the third model. So guess what is this? Third model. As of now, what we did, we can take up some sample IoT nodes with different directions at the base station. And second one, we tried by using that synthetic data set. And what is third one? Practical significance. And here in cell 4, in plotting functions, here we talk about, where is that plot diagram? This one. This one. So here, this entire snippet is about the function uses a polar coordinated system, which is natural for antenna radiation process, and it plots a beam lobe center at the predicted angle. And some next we talk about the role of IoT nodes. These nodes or devices are plotted as a blue scatter points around the circle. These positions represent where IoT devices are located relative to the base station area, as I explained. They help us visualize. So let's see, I try to execute this one. You'll get some basic idea in what way we are doing this one. Where is that? And how many frames we take? We stored everything data and now we're executing. Yeah, see here. So are you able to see this one? I hope it is visible to you, right?
Yes, sir.
Yes, sir.
Yeah. So here, as of now, what we explained, that blue dots are IoT nodes, and based on those base station nearby, that signal to noise ratio which is nearby, this red mark is there, right? It is the predicted beam. So we can show that there are more number of SNS ratio devices are there. We can go with the direction, and we believe that that is the optimized direction. Among those remaining beams, those things are optimized. And here I am showing in a particular 360 degrees way. So this is in what way we are combining IoT devices with these sample antenna systems, and based on the predicted beam, uh, we can imply the same thing with some agricultural applications, or we can employ the same a toy example with some other things also. And next combination is what? It is a small simulation with the frames of 18 I have taken because the system capacity is that much only. Now I am changing the parameters with a different set of inputs. No, not this one. Next one. What is that? What is that? What is that? Yeah, it's already completed, right? Yeah. So we take up the sample of channel 580. With 16 frames and 18 frames, that is also completed. Yeah, fine. So here we go with this example. I tried multiple examples. Most of these are failed only. For this session, I prepared some things. I almost spent 6 hours of time for this one. Anyways, in this case, here we talk about beyond beam direction in IoT and wireless networks. Performance is not just about which direction in the antenna points. Yes or no? What are the other parameters? Can you guess? In IoT, because we talk about what is the bandwidth and whether it is a narrow versus a wide beam or a transmit power, whether it is low or high, or some critical design norms like narrow beam, wide beam. Because based on the IoT device, effectively your AI model should need to change. Some of the devices they are maybe good at efficiency, they can have a more battery life. Some of the devices having very less efficiency or less battery life. So every time, based on the size, based on the capacity, your AI model should be adjust with those things based on the communication. So here, how to dynamically pick the best combination of uh, beam width and power in changing when, because as we know that IoT environment, multiple devices are coming with each other at the time they're communicating and revoking back again, joining again. So in our example, it is not possible to live data, but when I try to explain that, then you need to imagine that whatever the IoT device we have selected is not constant. Those configurations are not constant. For example, it is changing continuously. What is the best combination? That is that thing we need to look into upon. So it shows that this entire this particular thing is talking about a received signal strength indicator. That blue and that orange symbol. Blue, it is a static value, and that is different value based on the value. How can it changes? So here this code is all about how that receiver signal strength, that indicator naturally decreases with the distance, with some noise added to imitate real wireless channels. This creates a something like realistic input feature vector representing the IoT environment at any moment, right? So here dataset means when I try to download dataset, it is almost that size is more than 10 GB. So we need some, my laptop is not sufficient to work on that one. So if you have some good capacity computers, we can deploy that one. It will take some time, maybe 3 to 4 hours of time to generate those things. This is something about here. I try to compare in what way that static means without AI. If you look into where is that? See here with the static, we receive this particular coverage score. With AI, it is more. There is more accuracy. So here in this bandwidth and transmit power choices, these are discrete combinations. So here random forest classifier is trained enabling AI to learn what policy we pass at that one. So that means in case of static policy, I can say that always use a fixed setting. There is no change of, there is no assumption of adding of devices or removing of devices. That means whether it is a high device or low device, assumption is standard beam width and standard power, which is not recommendable, right? But in case of AI policy, it dynamically adopt based on the that state of RSSI, that the state of that indicator value. So based on this outcome, what can I say there? This particular AA based policy constantly achieves higher average coverage scores as compared to static policy. So we can prove that the adoption of AA. In previous case, we talked about static enable. Adoption of AA, which is sensing the nearby devices based on the device configuration, device capacity. It can estimate one score value. Based on the score value, it can create that particular AA policy, which can reduce the our resource, which can utilize the resources efficiently. That what we can say that this AA boss policy that is higher average coverage. We can say that. So here, this particular shows that the distribution of coverage of sources, this AA based system outperforms or perform well as compared to static beam management, proving that value of intelligence at the wireless edge. That's what is important. Value of intelligence. So this particular demonstration, the sample demonstration highlights that in Edge AI for real-time radio resource management, instead of human-tuned policies, because human-tuned policies means that is not compatible to some set of devices. For when device changes automatically, we need to change policy manual. The system blends optimal trade-offs between that width of the beam, or coverage, or energy consumption. So we can say that these things are directly applicable to either 5G or 6G IoT base stations, smart city deployments, or industrial IoT networks also. So hope you understand. See here my point is everybody not very good at coding. Here my intention is not executing the code, but hope you understand the flow, what is happening, how these IoT devices and AI models are combining and producing some better results. Is it so? As of now, it is clear. Okay, right. Next level in here I'm talking about in demonstration 3. As of now, we look into those beam directions and static distribution and AI distribution levels with respect to score. Here, in this demo 3, here I'm talking about the main purpose of here. The simulation is compare two network scenarios without adaptive beamforming, traditional antenna, omnidirectional, with adaptive beamforming, that is when AI come into the picture, I can say that AI driven smart antenna that points to active nodes, I can say that. So here in this demonstration, I try to compare these two things and in what way these two are we measure the delivery of packets through a proxy throughput across IoT nodes. So here a simulation setup is what I tried is first we take in first code I talk about IoT nodes, right? So we take for examples of 10, it may be 10 or 12 sample simulated nodes which randomly placed at different distances and signals from the base station, different signals. So here the traffic model is each node generates packets randomly, that is a probabilistic arrival per time slot randomly. But for that one, we use some random.rand function. We use that one. So here, the success probability of channel is depends on distance. If it is node is very far away from the base station, weaker signals. It is a common thing. Improves if the beam is directed at the node, it can boost some gain value. So here I'm talking about two things without adoption of AI, with adoption of AI. So with adaptive false one condition, with adaptive true one condition. Here I mentioned about. Here I talk about these things. I'm going to run these two scenarios. In case of without adoption, base station broadcasts equally in all directions. That is a weak signal to noise ratio at distance nodes, leading to low packet delivery. With the adoption of AI, the system calculates before taking the delivery system, the system calculates which direction has the highest packet demand, that is active nodes. The antenna beam is steered towards that direction, narrow or high gain beam. Nodes in that beam enjoy higher success probability, increasing throughput. So end of the day, When we are working with the signals, more throughput in right direction is important. So finally, I try to run this code. See here, as I said, here I'm comparing two things with adoption of AI, without adoption of AI. In case of non-adaptive, we received only the total delivered signals at 462. In case of adaptive, it's 510. So in this particular sample results, what is our take point? The total packets delivered with adaptive beamforming greater than without adaptive beamforming. Some nodes, especially at the edges, are further away from the base station. If you look at that one, it gives a dramatic improvements by in this bar graph. It shows that per node package delivered, the adaptive base are consistently higher than non-adaptive. So the point is here I'm combining. I try to show that how these IoT and antennas, IoT nodes, AI combining, and how AI learns traffic patterns, which nodes are active, which nodes are not active, and how the smart antennas, here smart means with adoption of AI antennas, they beam dramatically and IoT networks achieve better quality of service. That is, quality of service means in terms of throughput and reliability. These two are very important points while using the same spectrum. So this particular thing bridges theory to practice. AI-driven smart antennas can significantly improve either 5G or 6G enabled IoT in smart cities, or we can implement the same set of a code to we can it is a core code. We can replace with agricultural nodes, or we can replace with sensors related to health, or sensors related to temperature, sensors related to agriculture or smart system, whatever it may be, based on this base code, right? So this is something about what I tried. I hope it may help up to some extent for you. Uh, and this is not live data. By taking sample things, I try to compare with the throughput with respect to network, and in what way IoT systems are adaptive and non-adaptive and static and dynamic. So this is something about the demonstration process. And back to our course. Yeah. As of now, we done our this comparisons only, right? As of now, any doubts? My voice is audible to you?
Sir.
Yeah, right. So as of now, in section 1, uh, we talk about in what way this combination of adaptive means combination of AI and IoT, which leads to better results, which are compatible to modern networks. So here, I try to exemplify. I need just give me some 10 to 15 minutes of time. I'll wind up the session. So here, I representing different types of uh, predictive maintenance for IoT systems. So here, what is that one? Reactive planning. These things are most things. We start the most basic approach, which is reactive maintenance. So repair when malfunctioning. So whether it is good option or bad option. When, which is reactive maintenance or level 1. This is what we often call the run to failure method. Here we repair a machine only when it malfunctions. It's simple, but it usually leads to unexpected downtime, higher cost, and sometimes safety risk also. So that is called reactive planning. And in case of planning maintenance in level 2, in this stage, maintenance tasks are scheduled at regular intervals. So we maintaining uh, to implement this one, we need to maintain two things. One is the production environment, one is backup environment. In case of backup, we need to regularly for 2 months or 3 months, we initiate the process, and during the process, whether we are getting any failures or not. And in this case, the maintenance tasks are scheduled at regular intervals, like servicing a car, every 10,000 kilometers like that. So this helps reduce breakdown compared to reactive maintenance, but sometimes it means we replace parts or perform maintenance earlier than necessary. So hope you understand the clear difference between reactive and planned, right? In case of proactive, in level 3, it is somewhat advanced than planner. Here, the focus shifts to removing the root causes of faults initial itself instead of just fixing issues. So we believe that at that particular point of time, we are regularly getting problems. Just do not work with the fixes. You just remove it and go with the replace with a new thing. But it is somewhat cost effective as compared to previous thing. And final thing is that is predictive maintenance. What we talk about that one, it is more advanced than this one. This is the most better stage where we use cutting edge analytics. Analytics means in previous when we have a set of IoT combinations, whatever the results it is generating, based on the results, we need to conclude. Based on the conclusions, we take the decisions. So for this one, definitely we need that a combination of AI and sensor data to predict failures before they happen based on the previous trained data. That is, imagine if a machine telling us, I will fail in 2 weeks if you don't service me. That's predictive maintenance. It enables organizations to minimize downtime, cut cost, or maximize the reliability. So, in simple way, this 4-level figure shows the journey from reactive approaches when we wait for failure, not recommendable, to predictive approaches where we prevent failures using technology and data, and the exactly where modern industries now the coming healthcare industries or agriculture industries are heading with industry 4.0 and smart manufacturing. This is something about predictive maintenance. So most of the multinational companies are following the same predictive maintenance approach by using the AI automation process. Based on the analytics, they easily identify the average, the capacity of a particular device, and the average failure when will occur based on that one. It's simply to avoid the loss of data, to reduce the uh, cost, to effective utilization of the resources. So it's all about here. Also, I mentioned the same story. It is something about in detailed point of things in what way these IoTs and sensors and IoT-driven data processing is happened. The simple thing I explained is this particular IoT enabled predictive maintenance system. Predictive means which is used in the industry 4.0 applications, various different types of sensors, such as maybe that temperature sensors, a pressure sensor, or vibration sensor, or gap sensors. Many things are there. I don't remember all the things. So we need to monitor each every sensor with respect to machine conditions, and it is not manually. We need to train the AI models to continuously watch them. Their signals are processed through a converters and amplifiers. I'm not that good thing about these amplifiers and everything. That pass it to a controller system as I shown you here for real-time data processing. That is something about what I mean is it is combining real-time data monitoring with the cloud-based AI and automated control. The system minimizes downtime and reduces maintenance costs and ensures effectively and safe industrial operations. I'm not that because my background is computer science, so please excuse me for these converters and amplifiers and everything. Uh, that application point is my intention is in what way this predictive maintenance can be implemented in industrial operations with the adoption of AI. That is the point I want to share with you. And these are some of the case studies in specifically manufacturing case. So here I can say that this particular figure exemplifies about IoT use cases in manufacturing, specifically highlighting how connected technologies are transforming industrial operations at the core. That is, I can say that we need a smart IoT devices and safer IoT devices and more efficient process. So I can say that smart factory safety and wearable for safety which ensures, which supports those who are working there, uh, those who are, I can say that, employee protection. I can say employee protection by monitoring environmental conditions and employees' health in real time. This specifically this predictive maintenance leverages sensor data to detect equipment issues early, minimizing downtime and repair cost. Energy management. It I can say that power optimization. Uh, that is reduce the power consumption and reduce wastages, making operations more sustainable. Real-time quality control uses IoT-enabled sensors. And here I talk about digital twins. It is very important thing. These digital twins provide some virtual replications of machines and processes, allowing simulation and optimization without disrupting production. Right? It's showing that here it is the AR/VR also play some major role here. Here by using those things we can virtualize what will happen. uh, I can say that it is a prediction of future, sample prediction of future. So IoT automation, as I already explained, that streamlines repetitive tasks, while robotics and robotics enhance productivity, inventory management, and that is also important. What we call it as augmented reality supports maintenance, training, and tracking of uh, real-time digital overlays. Together, the use cases show how IoT revolutionizes manufacturing by enhancing safety. So the point is simple. Whatever things as I've explained, I try to narrow down with the manufacturing things only. And 6G networks, we already talked about that one here. We mentioned different combinations are there. And the main point of this particular figure, it is highlights a typical 6G structure, that is use cases as defined by the International Telecommunication Union, specifically radio communication sector. So it exemplifies some six interconnected domains at the center of future wireless networks. I can say that this is something in what way we can combining these transforming wireless communication way and key technologies in 6G networks. And it is all about something little theory only. And here I'm providing one more example related to smart agriculture. So here, in previously we demonstrated something. Here I try to relate with the same specific. We're changing the terminology. That's all. This particular figure represents an AI and IoT enabled smart farming framework that integrates sensors, connectivity, cloud computing. We are adding one more concept here. Cloud computing means we can share the data at anywhere point of time, and the data analytics to optimize agricultural practices. So sensors deployed in the fields continuously in paddy fields or in crop fields continuously capture live data based on the related to soil moisture, crop health. At the session starting, I explained the same thing, but here I'm showing a end-to-end block diagram in what way they are relating with each other. So whatever the data that sensors collected, this data is transmitted through connectivity solutions to cloud-based IoT services. From there, that AI extract, and we perform the data analysis on that AI, and based on that, we can take the decision. So for this one, we providing actionable intelligence directly to farmers by providing smartphones for timely interventions. Additionally, robotics UAV drones still may not be available. I'm not sure that one. So based on this one, this feedback what we receive the feedback loops between fields, sensors, and AV systems, and farmers helps in efficient resource utilization, improved crop yield, reduced manual labor, and some better, I can say that sustainable farming practices. This is the closed loop system demonstrate how IoT and AI together empower smart agriculture. That way, I can conclude this point. And here also I can mention in what way we can come changing way of farming. It is one of the point also. Again, same thing in what way I explained, but the previous thing also it is same thing. So these are the setup, and next case is a smart energy management system with IoT and AI. It is one of the application. Before that, I talk about what we called agriculture. So here, uh, if wherever you go, the common thing is receive the data and store the data and perform some analytics. But when application to application, things are changes, sensors are changes, devices are changing. So in this figure, I can say that it is about all a smart home energy management system that integrates various components which are useful to optimize power usage and efficiency, because every time it is not possible to manually off or on the systems. For example, if AC is working inside the room, if by using camera we can capture if no persons are there, automatically AC should need to off. When fan is working on that one, when no persons, when I scan the camera and no persons are there, I need to switch off the fan. That is automation process. So it shows that the various connections between modules are inverters and battery systems when I representing here. So they are linked with each other and smart grid through a smart method for two-way energy exchange. Finally, the system is managed by a AI analysis and a control unit that for automated and remote control via user-friendly. I can say that human machine interface, one combination interface, and a mobile application connected to the internet. We can use by using mobile phone also. We can look at that one. So here we use key technologies as you know, by using Wi-Fi. We use our mobile phones and we use some recent days we use some ACs also. So those Wi-Fi technologies are Zigbee technologies enable seamless communication between devices, while for real-time monitoring, support in the system. Sometimes even some kits are inside the home. We can access nowadays in most of the gated communities also. They're using those cameras, and by using mobile phones, they can simply switch on the cameras and they can see what is there happening, and whether those kits are or any other mischievous people that are happening or not. We can do that all the things. Next application is it is a smart water management market size. It is a sample we extracted from Swagger. So here we talk about in what way we adopted IoT and AI systems for smart water management. This is a sample picture. It illustrates the projected growth of the smart water management market from 2023 to 2032. As graph shows that in 2023, the market size is valued up to 16 billions USD, and it is expected to expand steadily and reaching 43 billions by 2032 as per their analysis. So what is the take point is the trend shows that in 2025 market expected to cross 20 billions. In 2028 it is about 28 and so on. This growth, because it is a necessity that we need to learn these things, and this growth is fueled by the need of efficient water usage, because without these adoption of AI technologies, most of the cities, you know that in Hyderabad or in Bangalore also, many times when water season comes, that winter season comes, we are not able to reservoir store that particular water content. And when season will come, when summer season will come, we lost most of the places also. Groundwaters are not available. So to do that one, we need continuous for effective utilization of water management. We need real-time monitoring, sustainability goals, and cost saving in utilities. And by taking these AI IoT automation process, um, we may expect that we can use those water efficiently with respect to different things. So it is flood monitoring system. So these are the some of the points. I can go with many common. Here I am providing some of the examples of these AI-driven design optimization, security and performance trade-offs in AI networks. Different applications. These all are applications. So this is something about uh, what is about my topic. So as you know, I start with my journey. In this one, it is all about AI-driven smart IoT antenna systems for real-world integration applications. So I try to address some of the things. I'm not able to spend all the things. I tried my best in what way with the sample set of code about how these antenna systems and IoT or AI trained models together improve the results. So you can take that based on the sample set of example. We can extend the same example to in our respective area, because many faculty members are working on our specific research areas. Some people are maybe working on agriculture, some people maybe work on health monitoring systems and everything. So I believe that this particular foundational session will help you in what way we can manage things, in what way things are happening, and in what way AI and IoT plays a major role for to achieve the sustainable goals. That's for the day. Thank you very much, and open to questions.
Participants are requested to ask queries. If you have any doubt, please clarify with Dr. Kranti Kumar sir. Fine, sir. Fine. Thank you very much,
Sir,
Dr. S. Kranti Kumar Garu, for
thank
delivering
you,
such
sir.
an highly informative and thought-provoking session.
Sir.
On behalf of
Thank you very much, sir.
Department of EC and all the participants of this AICTE-ATAL-FDP, I sincerely thank you for sparing your valuable time with us, and your
Sir.
contribution will definitely added great value to this FDP. Thank you very much.
Sir. Yes, sir.
Imran sir,
Yes, sir.
there is one question, sir, in chat box.
Yes, please, sir. Please go ahead, sir.
What is the question?
Sir, is it possible to know components in packaged food without no opening?
Mm, sometimes, but only to a limited degree, without opening the pack, because practical consumer steps, something like read the label, ingredients, and scan the barcode. Maybe look for certifications, whether it is certified by FSSAI or not. Or you can contact the manufacturer also. But some of the substances, we can take that. For example, if it is something like a milk products, it will give it. For example, it is spoiled. It releases a methane gas. If you have that type of sensor, it can capture that particular smell value, threshold value, and food consumption value. Based on threshold value, we can predict it, but it should be not in hot condition. Most of the times, IoT device cannot work for a different set of conditions. That is one possibility. Is that, yeah, it is up to, as far as my knowledge is concerned. Beyond that, maybe things are happen.
Okay, sir. Thank you, sir. Thank you very much,
Yeah,
sir.
Good evening, sir.
thank you, sir. Yeah,
Hello,
please.
sir. One
Yeah,
question, sir.
yes, yes, sir, yes, sir.
Sir, my name is Dr. Karunaya.
Hi, sir.
I completed PhD on antenna, sir.
Sir.
So,
Very
rectangle
good, sir.
patch antenna with DGS, sir. Different. I use 4 types of DGS
Okay,
using HFS. So
okay, sir.
which place we can use the AA, sir, in that design?
Sir, could you please repeat the question, sir?
So I completed PhD in rectangle patch antenna and topic rectangle patch antenna with DCS, sir, defective
Okay,
ground
okay,
structure.
okay, sir. Okay, sir.
So in that design where you can use the AI, sir.
Sir, AI is something like application oriented only. Whatever the data you are able to providing to that AI, based on that only, if you are providing the set of inputs or whatever the, for example, you are written about some thesis, right? So there, for our set of
Yes,
things,
sir.
whatever the inputs you pass to that one, instead of manual intervention,
Mhm.
whatever the data we received, we can work with. In our example, I talk about only one model. But the thing is, as a
Ah,
we need to do in a literature survey process, that we can take all the inputs we pass to algorithm 1, algorithm 2, algorithm 3, or some combination of hybrid algorithms. And whatever the results they are producing, we need to perform the comparative analysis. Among them, we need to select the best ones, the best combination. That only we can decide. But single agenda point of view, single algorithm point of view, we can't decide, sir. It is not possible.
Okay.
Yeah.
Okay. Only in documentation. only.
Hybrid models are possible, sir. Hybrid ML models are possible. They're advanced. That is beyond this topic. So
Okay.
if you are providing those data, I can suggest you something, sir.
So I completed PhD, but we can implement for that feature. How do you
Yes,
possible
sir.
to
If you mention that particular outcomes of your work, then we can design some future work. In what way we can combine that AML models to your work so that we can go ahead up to what extent can be possible.
Okay. So please share your mobile number or the Gmail ID, sir.
Definitely, sir. Definitely, sir. You can take from coordinator, sir, Imran Garu. He will share with you, sir.
Okay.
Thank you, sir.
Okay. Nice session, sir. Good.
Thank you very much, sir. Thank you very much.
Thank you very much, sir. Thank you.
Yes, sir. Yes. And since we are working on this antenna field getting huge data sets, only mainly possible, sir, it is possible to work with synthetic data, sir. For demonstration purpose, it is good, sir. But to achieve that sustainable development goals, synthetic data set is not possible, sir. We need a separate hardware for that one. For demonstration purpose, it is good thing. But in real time, when we want to do some societal impacted work, we should work with. You need to identify different set of IITs and NITs. Is there any massive volumes of setup? Or you can work with some third or fourth multinational companies. We can go as a internship there. We can take up those access, and there we need to spend some time, sir. Synthetic data would help, and I don't believe so, Mr. Kumar garu. Yeah. Right, sir. Thank you very much, and thanks for the opportunity for management and coordinator, sir. We will look into some more good collaborations in future. And if you are good with my area of research work, and my specific fields are quantum key management, quantum key distribution. So any participants, if are interested, and I'm working for Symbiosis University, we have a 600 journals, open access journals, and we can provide the free APC if you have any good work, and I can definitely associate with you. And you do not bother about article processing charge. We have open access journals related to all the fields. So if you're interested, please join with me. We can write some good research articles collaboratively. And I can share what I can do with respect to these AI models and the quantum key. If you have a data, ready available data, as Dr. Karunaya sir said that, if any predefined data sets, if any thesis works, if any things are available, let's share with each other, and we can join as a together collaborate to others. We can publish our work. I'm always open for that work, sir. Yeah.
Thank you, sir. Thank you once again.
Yes, sir. Yes, sir. So those who are reached you, sir, that Imran sir, please share my number. Let's look into some good collaboration, sir. Thank you, sir. Thank you very much.
Fine, sir. Definitely, sir.
Right, sir. Right, sir.
Right, sir. Thank you.
Yes, sir. Shall I round up the session, sir? Shall I close it?
Okay, sir. Sure.
Yeah. Thank you, sir. Thank you very much.
Okay, dear participants, with this, we came to the end of day 1 of our AICTE-ATAL Faculty Development Program. Today, we had 2 informative sessions, one with Dr. P. Nageshwarrao garu and one with Dr. K. Krantikumar garu. I hope all of you enjoyed the learning experience and found the discussions very useful. We'll resume tomorrow with day 2, session 3. And I look forward to your enthusiastic participation once again in tomorrow's sessions. Until then, thank you all. Have a pleasant evening. Good night. Then one more thing, feedback link is shared in the chat box. You can fill that feedback. Actually, it is the feedback come attendance. It is mandatory for all the participants to fill that feedback. Thank you once again.